All right, so I hope that you had an opportunity to start the related rate problems for homework. Did y'all run into any issues on those?
Yes.
Yes?
Snowball problem.
Snowball problem, okay. You want to talk about it? I don't.
The answer that we got 1 over 45 centimeters.
Uh-huh.
But then the book said the answer is 1 over 25 centimeters.
Hmm.
We just can't figure out.
Why, you were off by a factor of 2 there, huh?
It might be something with the way we were deriving it.
Well, you know, I think that might be a good place to start class. We just start with a very simple example. Which number was that? Number 11. Okay, snowball melts so that surface area decreases at a rate of 1 square centimeter per minute. Find the rate at which the diameter decreases when the diameter is 10. So you should have a general picture. You should have the instant in time. You should have what you're given and what you want and when you want it, right? I'm going through this quick because this was a homework problem. So I don't know if you drew a snowball, but your snowball. The snowball at the instant in time. At the instant in time, the diameter was 10 centimeters, right? All the way across, 10 centimeters. Maybe, did you use 5 for radius later? Okay, let's see here. And then in general, this would have an R, wouldn't it? Like a radius. And you're given in the problem, the snowball melts so that its surface area decreases at a rate. So for given, you're given the change in area, surface area, with respect to time as being 1 centimeter squared per minute. You're asked to find the rate at which the diameter decreases. So I'm going to say D, I want to use capital D for diameter, dt. And you want that at exactly the instant that the diameter is 10 centimeters. So that's the setup of the problem. And so you have to find an equation relating the surface area to diameter. And what formula did you use?
Surface area is equal to 4 pi of 1/2 d squared.
Okay, so it's the formula in the book, right? Did you use the formula in the book, or you just look it up online?
Surface area?
Yeah.
I just do it all.
You know it? Okay, so it's in your formulas, it's right here. In your formula sheets, reference page 1, you have some common geometric shapes. So 4 pi r squared is the area formula. Forgot the 4. 4 pi r squared. We're trying to relate area to diameter, so we replace r with what? The radius is half of d, and then squared. And then you have to actually square it. So did you square the 1/2 and get 1/4? Is that it right there? That's it? You square the 1/2 and get the 1/4. I was trying to figure out where that factor of 2 was going to come from, but that's it right there. So you can cancel this, and so you get area is pi capital D squared. That's your equation. That relates area to diameter. And now you do your differentiation implicitly with respect to time. So when you differentiate that, what does the left side become? dA dt. The right side, pi is a constant, so 2 comes out, 2 pi, d to the first power. So 2 came out, d, and then chain rule, take derivative of what's inside. The derivative of d is d dt. And that's it right there. Now you just plug everything in. dA dt was given to you to be 1. 2 pi, and then capital D. Now we can fix everything in time. This is going to be, what, 10? And then d dt is what you're trying to solve for. And so you get 20 pi here. You divide both sides by 20 pi. You get 1 over 20 pi is d dt.
So the question asks, like, how is the diameter decreasing? So is that why you wouldn't put a negative on that?
Well, what we would have needed to do if this was a melting snowball, right, is that our dA dt should have been -1.
It was a melting snowball.
Okay, so that dA dt when I wrote it down, if I would have used -1 instead, then our answer would have been negative. Remember I said on these related rates, sometimes you're going to get the same answer if the snowball was growing or shrinking at that same rate. You're going to get the same answer at that instant in time, regardless of if it's growing or shrinking. So this is the correct rate of change, just a matter of positive growth, and negative would be shrink. So 1 over 20 pi on a test would be fine. If you didn't put negative, I wouldn't take off anything for that. Units, though, we do need the units. This would be diameters measured in centimeters, and time here was measured in minutes, centimeters per minute. All right. Anything else on that homework? I've already been asked about number 14, which was the light pole problem, but I'm going to do one like that today. All right, so if you look at the board, I've got the animation there for the problem that I want to do next. And I did ask that you would watch the video, right, on this section at home. I hope some of you did. It's a plane flying overhead. And so if you just pay attention to the blue dot, notice that the blue dot moves across the screen at a constant rate. So the blue dot's not speeding up, it's not slowing down, it's constant, right? But then I also want to point out that even though the blue dot's moving at a constant rate, the measurement of this angle, this red angle here, notice, I know it's hard to see this, but notice how slow this is growing, 20, 30, 40, and then it gets real fast, and then it slows back down. I don't know if you caught that, 7, 8, 9, it's kind of slow, and then real quick there, and then it slows down. Do you see that? You can see it here too, like watch how fast right in there, how quickly it moves through the, like through the 90 degree, this part, it moves real fast through there, right there. And then the further I go out, that angle's still growing, right, but really slow. So the angle is not changing at a constant rate, even though the plane is flying across the sky at a constant rate. So this question says, you know, a plane is flying horizontally, altitude of 2 miles, a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment, the plane is 6 miles from the radar station. How fast is the angle of the tracking radar changing? All right. So very similar to the setup we had at the end of last class, right? We did a problem like this, but we were asking in that problem the rate at which the distance between the radar station and the plane were changing. This has to do with angle instead. So we'll still set up our two pictures. You still have a radar station. You still have a plane. And that plane is moving at 600 miles per hour. But this time I'm interested in the angle, right? The angle. So let's refer to that angle as the angle between this line segment and the ground, right there. Let's call that angle theta. That's what we're interested in, right? That theta is changing. The only other piece of information I have that's always the same in this problem is the height of the plane, right? Is always 2 miles. That side never changes. It's constant. Now, the instant in time we're talking about, what can I fix? The hypotenuse, this is 2, right? At the instant in time, the distance between the plane and the radar are what? It says it there. At the moment, the plane is 6 miles, so I can fix this side right here as 6, right? Sometimes people make the mistake of using this as 6, But that's not the distance between the plane and the radar station, right? That's the distance between the projection of the plane onto the ground to the radar station. It's not the same thing. So that's my instant in time, right? I'm given what? What am I given here? 600 miles per hour, right? Yeah. Which is the rate of change of the plane. So I know I have a derivative here. 600 miles per hour is a derivative. It's the derivative of something with respect to time, but I need to figure out what variable it is. It's not theta, right? What is it? X. That's what we called it last time, right? We said that this, you could almost create a triangle this way and call this side x, right? And that would be the same as calling this side x. So the rate at which x grows is the same for the upper triangle as the lower triangle, right? Now, if I do it this way, and I want to get my signs right, then I need to look at this as being what? A negative number. Because it's shrinking, right? X is shrinking. As the plane moves this way, this distance gets smaller. Any questions? No? What do you want? d theta dt, right? The rate at which the angle is changing. So I want to know how fast theta is changing. When do I want that?
At 6 miles.
At what 6 miles?
From the radar station.
Yeah, and I don't have that labeled in my problem, do I? It's not theta, right? This is not when theta is 6. This is when that distance between the two is 6. So I need to at least label it. Let's label it h. And that way we can say when h is 6. Is that fair to you? What type, or what equation, what variables does my equation need to contain if I'm going to connect these two together? X and theta. So you look back over here at this picture, your general situation, not your instant. You try and come up with any equation you can think of that connects x and theta together. Anything that connects x and theta. So this and this. What did I hear? Cosine? Cosine is going to be, cosine of theta would be adjacent over hypotenuse, right? Which would work, yes?
Yes.
But you would have theta, x, and h in there, right? And let me write it down just so you'd see it. Cosine theta would be x over h. If I take the derivative in here, right? If I do, because of chain rule, does everyone agree I'm going to get a d theta dt to come out of this somewhere? I'll get a dx dt to come out somewhere. I'll also get a dh dt to come out, won't I? And I don't have any information about dh dt, do I? So although that formula would work, that variable is going to cause a problem. But we could possibly not have to use h if we use 2 and x and use a different trig function. See, because the 2 will never change, will it? So instead of cosine theta, sine would be opposite over hypotenuse. We would want tangent. Tangent of theta, write this down. Tangent of theta would be equal to 2 over x, opposite over adjacent. Let me ask you, could I use this also? I mean, this will work, but could I use this? Yes, I could. It's your choice. All right, but I'll stick with tangent because I think most people would have done tangent, right? All right, at this point, we have the equation. We could differentiate right now. But I'm curious to see what you would do for the derivative here. Like looking at it and thinking ahead a little bit. Like the derivative of tangent theta everyone's going to be comfortable with? What about this side? How are you going to take the derivative of that side? You could do like a quotient rule, couldn't you? You could also pop the x up as an x to the negative 1, right? Which I think is the way to go. So before I take a derivative, let me just write it this way, right? And then come in and take the derivative. So here it comes. Derivative of tangent theta is secant squared theta. Very important step. Times d theta dt. Because you have to take derivative of tangent of something, which is secant squared of that something, times derivative of the inside. This is chain rule. And then on the right side equals, this is power rule. So negative 1 comes out, comes negative 2, x to what power? Negative 2, am I done? No. Times derivative what was there? dx dt. Now, in order to be sure I've got this, I need to look at that derivative, and I need to make sure everything I have is in there, right? So what were we at? We were looking for d theta dt, weren't we? It's right here. We were given dx dt. That's right here. We were also given, we wanted that when h was 6. Well, h isn't in here. I have x in here, and I have theta in here. Those are things that I don't have right offhand, do I? But I can fix everything in time now. And if I fix this, could you solve for theta here? Yes? Could you? Okay, and what about this side here, x? Could you solve for x? Yes. So because I need x and I need theta, I'm going to go solve for both of those using my instant and time picture. So help me get theta. Were there any questions? What can I use to get theta? Sine? You know that sine theta is 2 over 6? Or in other words, sine theta is 1/3, right? What is, I mean, I could solve for theta here. Couldn't I do like arc sine on both sides and go pre-cal style here? But I just want to know what secant theta is. Isn't secant the reciprocal of cosine? Yeah. So if I had this side here, wouldn't I know what cosine is? And then I would also know what secant is. So it looks like knowing that x would really help me solve that, wouldn't it? Or solve this. Let's get x. So I'm going to say here, let's wait for a second. I'll come back to this. Let's get this. This is x squared plus 2 squared must equal 6 squared. So x squared must equal what? 36. Take away 4, so 32. So x is root 32. So this triangle becomes this, root 32. Now let's see if we can actually write this equation out now. I think it'll be a little easier. Secant of theta, but then square it. So what is secant theta? Square root 32 over 6 is cosine theta. So 6 over root 32 is secant theta. Do you all understand what I'm doing? So I'm just flipping over what cosine is. So I'm supposed to take 6 over root 32. That's secant, and then square it. So what would happen when I square 6 over root 32? What would it? Maybe I'll write this down. 6 over root 32, that's secant theta, right? Squared times d theta dt, which is what I'm looking for, equals negative 2 times x to the negative 2. What's x? Root 32 to the negative 2 times, what's dx dt? Negative 600? Isn't that what it was? See, look, everything has been plugged in except one thing, d theta dt, and that's what I'm trying to solve for. right, so now square this. You get 36 over 32 times d theta dt equals, what is this? What is root 32 to the negative 2 equal to? 1 over 32. So you drop it down, then you square it. So this is 1 over 32. What's negative 2 over 32? Negative 1 over 16. Times negative 600 times, oh, that's it, right? So I hope you're following that. It's just some algebra. Drop that down. 1 over root 32, square it, becomes 1 over 32 times this, and then times 600. I think that cleans up a bit, doesn't it? 600, 300. Ugh, I don't feel like doing this. 36 times 16 over 32 times 600, and that's a negative. This is d theta dt. So all I did here was just took this, it's negative, negative, sorry, positive. This is negative times negative, it's positive. I took that fraction, multiplied by the reciprocal on both sides.
If you would have just left it as 1200 over 32 and 32 canceled and divided by,
Leave it by, wait, by what?
back at this point when you were multiplying the right-hand side, it would have been 1200 over
Oh.
32.
Oh, yeah.
32s would have canceled when you divided it.
Yeah.
Giving you 1200 over 36.
Yeah, I mean, there's a lot that is going to cancel here. I mean, however you do it, it's really up to you.
With the fraction on the left, when you multiply it over, would it flip?
Which one?
The 36 over 32 on the very left?
Oh, wait, I did the other way. I'm sorry. That's why y'all are looking at me. D theta dt is on this side. Sorry, I need to move this constant to the other side. That's why y'all are. All right. Apologize. Okay, this right here was 600 over 16. And then I bring this, flip, and multiply 32 over 36. Is that what you were saying? Yes, okay. Sorry about that. So when you do those, you should get 100 over 3 reduced. Anyone get that? Yes? Which is 33.33333. So you're getting d theta dt is approximately 33.3. Yeah, so what does this represent? How do we measure theta? How do we measure time? Let's do time first. What was time measured in this problem? How was time measured? Hours? So what is it per hour? So you think degrees, right? But degrees were never given in the problem. So whenever degrees are not specified, your answer is always in radians. So this is radians per hour. At that particular instant, your angle is changing at 33 radians per hour.
Wouldn't put like that little line above the 3?
The what?
Wouldn't put that line above the 3?
Oh, you could, yeah. Well, I didn't because I said it's approximately, so I'm rounding it. If I wanted equals, I'd have to put the bar over. What? Okay. So let's see here. Okay. Does that make sense, everyone? Yes? Any questions on that? All right, let's take a look at the next one. I believe this is similar to number 14. Let's see, 14, right mounted, home man walks away. Hey, it's pretty much the same problem, I just changed the numbers around. So a street light is mounted on a 20-foot pole. A 6-foot man walks away from the pole at a speed of 7 feet per second. That's pretty brisk walking, isn't it? These are long strides. How fast is his shadow moving along the ground? relative to the pole when he is 12 feet from the pole. So here's my animation here. Can we kill the lights, just the one over here? Yeah, there we go. So there's the man. There's the light, right? So when the light emits from this point, and you have a shadow cast on the ground. So from that point, anything blocked by him is shadow, right? And it gets projected onto the ground in front of him. So this black part right here is shadow. And as he moves away from the pole, the length of his shadow is changing as he moves, right? He's moving at a constant rate. Look at him. Look at the red. It's just moving across, right? The shadow is growing. We want to know at a specific instant in time, right at that instant, right there, how fast is the tip of his shadow moving relative to the pole? How fast is it moving across the ground? Understand? Now, I already kind of gave away a lot of the problem with my drawing, right? That wasn't given in the problem. I didn't draw a picture for you. So, do you think you could have come up with that drawing on your own? That's kind of a question you have to ask yourself, right? Could I have done that? Because your general picture, you've got a pole, it's 20 feet, you've got a man, it's 6 feet. Do you think you would have realized that his shadow is a point that connects out here? You think you would have got that on your own? Huh? What's that? He's a 6 foot pole. I mean, he's a 6 foot man. He's a 6 foot man. He's moving at 7 feet per second. So he's moving, right? Does everyone think they could have gotten that much of it? Why don't we call the shadow, this length right here, why don't we call it S for shadow? Is that all right? S for shadow? Kind of looks like a 5. See, there's no particular perfect way to do these every single time. You just kind of start to piece things together. What's the instant picture look like? He's 12 feet from the pole, right? So this distance between here and here is 12, right? His shadow is something, right? Not quite sure what it is on the ground. Still going to call it S? Oh, sorry, I labeled this X. It's actually what, 12? I was getting ahead of myself. Because if this is 12 in this picture, I should give it some label over here. And I would call it X. Because it's changing, right? At the instant in time, it's 12. The 20-foot pole doesn't change. The line connecting the two does change, right? This line connecting that. Also thinking about what I'm given and what I want. What am I given? dx dt. I'm given the speed the man is moving. The speed the man is moving is the speed that this point on the ground is moving in this direction, which would be the rate that x is changing. So I'm given dx dt. Following? What do I want? What do y'all think of that? Yes or no? It's actually no. And so that's why we need to discuss this. This is about relativity here. if I'm moving, right, at 7 feet per second and I'm watching my shadow grow, then that shadow is growing relative to me, but I'm moving. The pole is stationary, right? So relative to the pole, the shadow is actually moving faster than relative to me. It's kind of like, if I'm standing here and I'm on a car going to, 100 miles an hour down the road and I shoot a bullet, then the speed that the bullet is moving away from me is slower than the speed it's moving away from someone who's standing on the ground. Because I'm moving also. So what we want is not ds dt. We actually want that rate of change, right? This whole distance. How fast this whole thing is changing from that point to that point. Which is what? We could call it a new variable. We could. But it's really just x plus s, isn't it? This is really just x plus s. And what we want to know is how fast x that's changing, right, with respect to time? So couldn't I do this instead? Don't I want the rate with respect to time that x plus s is moving? Now, I know that that looks weird. But this is the derivative of two things being added together, isn't it? How do we take the derivative of things if they're added?
Just take the individual.
Individually. So isn't this just dx dt plus ds dt? And does that make sense to you that this is what we want? Yes? We want not only, it's the speed of the shadow relative to the pole is not just the speed of the shadow relative to the man, it's the speed of the shadow relative to the man plus the speed of the man. If that hopefully makes sense. If s is only this distance between the man and the shadow, the rate at which that changes, you have to tack on how fast x is changing. Yes or no? You have a question? Or I'm seeing nodding and yes, but I don't know if that means like no. Like no? No means yes, no, yes means no.
It makes sense when you explain it.
Okay.
I don't know that I could have come up with that,
Okay.
but it makes sense when you explain it that way.
And that's the way these problems work. I try and show you as much as I can. Every problem's unique. And you just, slowly you kind of chip away at, approaching these things and getting everything in order and thinking through them. Is there a specific moment when I want this? At x is 12. That's exactly the moment. Because you have to figure out not only what you want, but exactly when you're going to fix it. Like when you're going to stop the clock, freeze everything real quick. I think I have everything I need. I don't know. We'll see. I have to relate what variables together. X and S, really. I mean, those are the only two variables in here, right? X and S. I mean, dx dt, don't I already know what that is? I mean, that's 7. That's given to me. So I really just need to know ds dt, but I have to add 7 to that answer when I get it. So just connect S and X together from this picture.
X plus S.
X plus S.
Cool.
So you have to be able to relate X and S together somehow, some way.
20 over 6 is equal
20 over 6 is equal
to x plus s.
to what?
X plus
X plus
s
S
over s.
over S. What the heck is that? It's proportional? You're using similar triangles. That's what we have here. So let me try and help everyone see that. Look at this picture. I have one big triangle, X plus S, and I have 20. And then I have a smaller triangle that looks like this, 6 and S. And these triangles are what we call similar triangles. Similar triangles have the property that all the angles are the same. So everyone agree that this angle is the same as this angle, right? They both share that same angle. They both have a 90-degree angle. That's this. And if this angle and this angle are the same, then that third angle has to be the same in both of them, right? Because all the angles of a triangle have to add up to be what? In two-dimensional space. In Euclidean geometry, yes. 180. So if all the angles of a triangle are the same for two different triangles, then they are what we call similar, which means the ratios of the sides of congruent sides, ratios of the sides are equal, basically. So if I take this little short side of this triangle and divide it by this little short side of this triangle, that ratio should be equal to the longer leg of this triangle divided by the longer leg of this triangle. Is that the only ratio I can set up? I can set up any ratio as long as they're corresponding sides. So I could use that. I could also use, let me see, I could go 20 over x plus x plus s equals 6 over s. Right? Short over long on this triangle equals short over long on that triangle. I can use that one. I could use, someone give me another one I could use.
X over S. Oh, yeah.
X
I mean, X plus S
over s equals 20 over 6. Oh, wait, same one. Okay, so let me flip it. Could I do this? S over x plus s equals 6 over 20. Yes, I mean, there's a bunch of different combinations, right, of what I could use. But that's the relationship that I get. This is the equation connecting them, using similar triangles. And we have to differentiate these, don't we? We have to differentiate these. I'm going to stick with the original one right here. And I'm going to do something before I actually differentiate. First of all, I'm going to reduce the left side to become what? 10/3? And then again, before I differentiate, I'm going to choose to do a cross multiplication to get rid of the fractions. So I multiply both sides by s. I multiply both sides by 3. So I get 10s equals 3x plus 3s. Do you agree with that? And I can actually subtract 3s from both sides and get 7s equals 3x. And I can differentiate that. What's the derivative of the left side? 7
DS.
times ds dt equals 3 times dx dt. What were we trying to solve for? Like, what were we trying to figure out? ds dt basically is what we wanted, right? Do you know dx dt? Yes? It's 7. So I actually can say right now that 7 ds dt equals 21, which means ds dt is what? 3. 3 what? Feet per second. Now there's something a little more subtle I want you to understand here, because this is really an important thing. What have we not used? I mean, I set up the triangle, got the equation, and differentiated. Here we are. I'm trying to solve for ds dt. I was able to solve for it. I have not used what, though? The what? Well, I used it for the 7, didn't I?
We haven't added 12.
We have not used the instant in time, the 12, have I? X is 12. And that's because in my derivative, did x ever appear? No. What does that mean? It's irrelevant. It's independent. In other words, the speed of the shadow is what? 3 feet per second. regardless of where the man is. That's kind of weird. Isn't that kind of weird? I mean, if you look back at this picture, the calculus is saying that the speed of the shadow is constant. How fast is the shadow moving relative to the man? 3 feet per second. How fast is the shadow moving relative to the pole? 10 feet per second. Well, how fast is a man moving? 7 feet per second. But his shadow is moving at 10 feet per second. So the shadow is always in front of him, right? Just imagine, now it's not a shadow anymore. Just imagine it's two guys racing. One of them walks 7 feet per second, the other one walks 10 feet per second. The guy who's 10 feet per second is always going to be in front of the guy who's 7 feet per second, right? He's going to be moving away from him at a total of 3 feet per second. But in this weird geometry problem, I don't know, for me this has always been kind of like a head scratcher. Like, I always would think that the further you get out, the faster the shadow goes. Like it has to, because it gets longer and longer, right? So to me, it just seems like the shadow should be getting longer the further out I go. But the calculus tells us that no, it's actually moving at a constant rate. Which I think without the calculus, you could probably have decent arguments for both opinions, right? But this settles it. There's no debate. All right.
So your answer would be?
So the answer. So what's the answer? This was just ds dt, and I was able to say, wait a minute, hold on, there's no x in there, so wow, this doesn't matter where the guy is. Now the final answer is that, relative to the pole, the speed is dx dt plus ds dt, which was 7 feet per second plus 3 feet per second, which is 10 feet per second. And maybe it does make sense. If you look at the tip of the shadow, just the tip of the shadow, and just watch it go across, it's moving at a constant rate.
Yeah,
It's not like it's not like going slow and all of a sudden speeding up. All right. We good? Questions?
So if the man was accelerating, then the shadow.
Now, that would be different. Yes, if the man was speeding up as he went, then that. But we're going to assume in all these problems that at least one thing is a constant rate. If it's not, then it becomes much more difficult. Okay, so a conical cup is which is 4 inches tall and 6 inches wide, is sitting there inverted. You've seen these, right? Little water jugs, you pulled out the little paper cone cup, right? Okay. So assuming that we are filling that, we're pouring into it at a constant rate. How fast is the water level rising when the water is 1 inch from the top of the cup? So here's our picture. And what happens if the water is going in there at a constant rate? What happens initially? The water level is going to come up fast, and then what? Slow down as it gets higher. So let's see if it does. Because of the geometry. Oh, there it is.
So it's kind of
Why is it freezing?
It's kind of like that paint problem we did.
The paint problem?
Yeah.
Yes. It's something like that. Yes, it is. Yeah. Trying to figure out why this thing looks like it's getting hung up. So I have the program written in a way that it is filling up the volume at a constant rate, right? And you can see that at the end it's coming up real slow, right? Real slow. I believe I can also, I have another animation that's a little better than this. Hold on. So this is basically the same picture. What I want you to see here is this blue curve is the representation of the volume, okay? Or sorry, the height of the cone. Now, you know what, now that I think about this, this is a different problem. It's measuring height. The height's coming up. You know what, I don't know what it is. Now I look at it, I don't want to. No, that looks like the right problem. Yeah, because in our problem, are we wanting to know how fast the water level is rising? Yes? Okay, so the same sort of issue here. So the water level is called the height. So if this is the height as a function of time, the dh dt is the slope of the tangent line. So look over here at the very beginning, look how steep this derivative is. See how steep it is? That's a very fast rate of growth. But as time goes on, it starts to flatten out, slows down. All right, there it is. Let's get to this. All right. What do you want to start with? Should I bring the problem back up here so you can at least refer to it?
Yeah. Well, we can start by drawing a cup.
You can draw a cup? All right. So your general picture. Okay. Instant picture here. Same cup. So anything you want me to label on either one of these pictures?
Well, we
Do what?
The water level?
You want to draw? You want me to draw a water level? All right. Something like that. That's changing, right? In the picture. I mean, as time goes on. What else?
the dimensions of the cup.
Dimensions of the cup. How wide is the cup? 6 inches. Now, is that going to change?
No.
No, the cup doesn't change, right? Well, I hope not. That'll change the problem, right? That's 6. How tall is the cup? 4. That's never going to change, right? So I can do the same thing in this picture. I guess my picture's not drawn to scale, right? It's not proportional. What else? H and R. So height of the water, because we're interested in the height, right? How fast is the water level rising? So we should label that water level. I'll label it right here. This right here, this distance is changing, so I will call it H. Agreed? And then what?
And then the radius of the water, like the top of the water?
The top, you want the radius of the water?
Or the diameter?
Now, I agree we're going to need it, but I don't understand why right now you would want that. I'm trying to go logically, like as someone's thinking through this. Like, yes, we will need it, but
It'll be changing.
it will change. But we're not interested in that change, are we? We're going to need it. Okay, I'm not disagreeing with you, but I think naturally someone looking at this problem first time isn't going to want to just draw R necessarily right away. We're going to have to, but I mean, I think having H is good enough. We want to know how fast H is changing, right? Do we know an instant in time here? How fast is the water level rising when the water is 1 inch from the top? So hold on, everyone. Sir? Sorry to interrupt you. So what do I put there then?
Sorry, I was lost.
Okay. No idea? No? No? Sir?
Maybe the volume?
The what?
The volume?
Okay. No? Just trying to figure out what's going on over there at that table. I continue to have distraction issues over there. So, Anybody else? What I should label H to be?
3 inches.
3. Because what?
From the top.
It's an inch from the top. So it's a little tricky in the wording there, right? An inch from the top. People will make the mistake of saying, oh, I want to know when the height of the water is 1 inch. No, it's from the top. So that means that's 1 inch. If the total is 4, then that's got to be 3. Understand that?
Yeah.
Okay, so a little tricky in there.
I was like, where'd you get that?
Would you all agree, like that's probably, if you're just first setting up this first time, like that's what you would look at, and that's pretty much a lot of the information right there? All right, what is it that you're given?
The rate is 2 pi
The,
cubic inches per second.
the rate of what?
The rate of the water being poured.
Okay, so what unit of measure is that? It's volume? 2 pi cubic inches per second. Cubic inches is a measurement of volume, right? Water's being poured in. That's a change in volume with respect to time, isn't it? So they're giving you that dV dt, water is coming into this thing at 2 pi cubic inches per second. What we want is,
How fast is it rising in water is at 1 inch from the top?
okay, so how fast is it rising? What is the it for us in our picture?
H.
H, right? Isn't it H? H is the height of the water. So we want to know how fast that H is changing with respect to time. We want to know that at exactly the moment what? H is 3. That's all. I think that's it. So I think we need a formula now. We have to connect what two variables together? The height and the volume, right? The height and the volume.
Does it have to be for a cone? Right? I mean, obviously, then.
Well, it would be most likely the cone because that's the geometric shape we have. So, well, we've got this information down here. Okay, we know what we want. We know what we're given. We're trying to connect V and H together, and
It's already done by the formula.
okay. So you're looking in the book for the formula. The formula for the volume of a cone is 1/3 r squared h, right? That's the volume of a cone according to your book, and this is what r is this radius, and the height of the cone is this, right? Okay, I agree. This is a good formula, right? The only problem with the formula is that it includes what? R, which means if I differentiate, I'm going to have a dV dt in here, right? Because I have an R in there, I'm going to have a dr dt. Because I have an H in there, I'm going to have a dH dt. dH dt we want, dV dt we're given, dr dt we know nothing about. So we need to somehow try and eliminate the R from the formula. That would be nice, right? Also, I want to point out that when we're looking at this volume formula, we are not looking at the volume of the entire cone, right? We are looking at the volume of the water, right? The volume of the cone is fixed. It's not changing. The volume of the water within the cone is changing. So don't be like, oh yeah, no, I know the radius is what? 3, and I know that the height is 4, and there I got the volume. Well, you're not doing any derivatives that way, right?
So this would be another proportion problem.
Exactly. This is another proportion problem. So
And 1 would be X.
how would you get your proportion?
6/4 equal to
3 over X.
Yeah, so this is where you're going to have to draw some triangles. So you pull out your sword and you cut this thing right down the center. Cut your cone, you split it open, you look at a cross section of it. Right? So imagine just cutting that cone right down the middle along a dotted line that goes right through the center. If I do that and I peel it open and look at it, won't it look like this? It's now 2-dimensional instead of 3-dimensional. This is my water level. I'm going to draw it as a straight line though. That's what I would have. And then I would have the center like this. I'd have two right triangles over here, wouldn't I? And now, let's see. I don't need this left side, so I'm just going to draw this. Water level. Well, here's my water level. There it is. We know all the way from here to here is what? 4. We know all the way from here to here is 3, right? We know from here to here is H. Can't fix it yet, right? Can't fix it yet. That's H. And then from here to here is what? R. And we don't know what that is because it changes, right? As the height changes, the radius changes. Do you see why, yes, R needs to be there, but it's naturally, it doesn't show up until really here. So you see your similar triangles?
So first, you could do the Pythagorean theorem to find out the length of the hypotenuse, right?
If you needed it, but do you need it?
I guess not really.
You don't really need it for this. I mean, you could figure out what this length is and this length, but you don't necessarily need it to set up a proportion. Remember, where we are is we have a formula for volume, 1/3 pi r squared h, right? That's what we have. We don't like r being there. I would like to rewrite r in terms of h. I'm going to use this relationship to rewrite that r in terms of h. So what similar triangle ratio can I set up here? There's a bunch you could use, but what? 3 over 4 equals r over h. Because you haven't taken a derivative. If you haven't taken the derivative and you fix everything, then nothing's moving, and you take the derivative, it's going to be 0. Should be, because it's not moving. Right? So what is that going to allow me to solve for r in terms of h? Is that the correct proportion? The short side of the big triangle over the long side of the big triangle is equal to the short side of the little triangle over the long side of the little triangle. If I multiply both sides by h, I have an equation that has r in it. And then that can come back in here, right? This equation only works for this cone, right? This cup. If I change the cup, this proportion changes.
Right.
So now my volume formula that I was trying to get is 1/3 pi r, which is 3/4 h squared, right? And then times h. Now do you have an equation that has just v and h in it? Yes. And so you're in business if you differentiate it. But I'd definitely like to clean it up first. I'd like to square out this thing first. So volume is 1/3 pi times 9/16 h squared times h, which is volume equals 3/16 pi times what? H cubed. And I think that's going to be a pretty clean formula to differentiate. Yeah, go ahead. You get what? dv dt equals 3/16 pi. You want me to just bring that along for